Modern jets such as the 787 and A350 exemplify the switch to composite materials for fuselage construction. This seems set to stay as the way forward for new aircraft designs. Although there are challenges, the lower weight of composites offers significant improvements in efficiency and operating cost. Let's take a look at composite versus aluminium fuselages. Did you know that aircraft have not always been made of metal? Many early aircraft, even those for passengers, used wood and fabric, and not just small aircraft such as early biplanes. The wooden Howard Hughes H-4, known as the Spruce Goose, was one of the largest aircraft ever built. It flew once, but never entered service. Low cost and somewhat low weight, wood was practical, but it was not strong enough for very high-speed flight. As speeds increased and certainly as jet engines were introduced, metal became the better option. With its low weight, low cost and relatively high durability, aluminium was and has been one of the best choices. While titanium is even better, it's too expensive. The compromise has been to use aluminium alloys to reduce the issues of stress fatigue and corrosion. Such alloys have formed the basis of all jet aircraft fuselages until recently. Small amounts of other metals, like steel or iron, can be included, but on their own are too heavy and would stress at high temperatures. Modern aircraft like the Boeing 787 and Airbus A350 have shifted to composite materials for construction. This follows the trend towards more efficient and lower emissions aircraft operation in recent years. Interestingly, earlier aircraft had already started to move this way. The A380 is approximately 20% composite and the 777 around 12%. Interestingly, the new 777X will retain an aluminium fuselage like its predecessor. Composite refers to construction from two or more different materials that when combined perform better than the elements by themselves. For the 787, around 50% of the materials used are carbon fiber reinforced plastic or CRFP and other composites. Aluminium still accounts for 20%, titanium 15% and steel 10%. Airbus, which also makes use of CFRP in the A350, describes the material as follows. In CFRP production, thousands of microscopically thin carbon threads are bundled together to make each fiber, which joins others in a matrix held together by a robust resin to achieve the required level of rigidity. The composite component is produced in precisely shaped sheets laid atop each other and then bonded, typically using heat and pressure in an oven called an autoclave, resulting in a high-quality composite. Much of the credit for the move to composites is due to Boeing with the new clean-sheet aircraft design of the 787. This was lower capacity than the 777 and moved Boeing into the unproven market for a composite airframe. Airlines reacted positively, though, so much so that Airbus chose to revise its plans for the A350 and also design a new clean-sheet composite widebody with the A350. In addition to weight reduction, such materials are also less susceptible to corrosion and fatigue, reducing maintenance time and cost for airlines. This resistance to fatigue has also allowed for larger windows, as seen in the 787 and A350. Composite structures can be molded into any shape, allowing for separate entire fuselage barrel sections to be made in different locations rather than aluminium sheets that needed to be bolted together. Cost can be a drawback to a certain extent. At this time, CFRP components are more expensive to produce than standard metallic parts, but over time this can be offset by lower maintenance and operating costs. There have also been concerns raised about the detection of damage to the fuselage. Impact damage is not as visible or easy to detect as it is on a metal airframe, although other tests, including optical, electrical and acoustic, can check for airframe damage. Fuselage modification is another challenge. This has been raised as an issue with freighter conversions. Cutting a cargo access door in a composite fuselage is more challenging than in an aluminium one. It may be easier for a possible A350 freighter, though, as its fuselage is constructed from composite panels rather than complete barrel sections. But with the savings in weight and improvement in efficiency, these drawbacks are likely ones that operators are happy with. Do you think composite structures will be standard in the future? Or will aluminium always have a place? Let us know by leaving a comment. In addition to our daily YouTube videos, Simple Flying publishes over 150 articles and a podcast every week. If you're looking for the latest aviation news and insights, visit simpleflying.com. Thanks for watching, and don't forget to like and subscribe before you go.